So, today we're going to be talking about shrinkage and admixtures as well as concrete properties. But before we do that, I'm going to conclude what we were talking about last week with questions 5 to 8. So there was a few questions we didn't get to finish last week, and also this room. I think the tech in this room is like supposedly fixed. I think the camera doesn't work still in this room, but I can charge my laptop now, so we're not going to run into the issue of me running out of power again. Is this microphone working? If I talk here, is it okay? All right. So continuing from last week, so back into the headspace of slump and things like that. So I'd like to explain this table a little bit better. So the way that the question frames this is describe the slump test method for the measurement of concrete workability. What range of slumps is required for normally reinforced concrete members such as slabs? Okay, so here's where I'd like to elaborate a bit more, just checking I'm on the right document, about this table. So I briefly showed this last time, but the idea is that when you order concrete, you can specify a few things, as I mentioned last time. You can specify concrete strength, the volume of concrete you're ordering, as well as the workability. Okay, so you can describe it as very low workability, medium workability, or high workability. Now, for this particular question, they're saying if we're ordering concrete for a slab and we want a medium degree of workability, the target range of slump would be somewhere in this ballpark. So 25 mil to 100 mil of slump drop. Yeah, when you do the slump test, okay? The thing that I didn't really explain last time was the compacting factor. So that's another column in this table. But the idea is that the compacting factor is the ratio of weight for when your concrete is partially compacted versus fully compacted. And in this context, compaction is talking about the concrete vibration. So I don't think I really mentioned this last time either, but as you pour concrete, right? So you've got your boom pump, let's say, and then it's spewing out your concrete. The idea is that you'll have some workers on the other side, and there are various tasks. These are the concreters, and they will always have at least one person who does the concrete vibration with a concrete vibrator. And this is like a little stick thing, and it just vibrates the concrete, and it pops all the little air bubbles, and it makes the concrete more uniform. That's one thing that it does. So these air bubbles get eliminated as you're pouring it, and so you have essentially less voids in your concrete and more solid, I guess. But it also increases like the workability, I guess, of the concrete. So it will make the concrete flow more, right? Yeah, I'm trying to think if there's anything else to say about that. Not really. You don't want to over vibrate the concrete though. That's pretty important. So there is like in like the building methods code. So the code that we're going to be mostly talking about in the context of this course is AS 3600, the 2018 edition. So this is kind of like a designer's guide to reinforced concrete. But when you're doing the placement of concrete as like a site engineer, you're following kind of different, I think it's either Australian-wide, so like a federal government requirement, or state government. So if it's state government, like I remember it is, New South Wales has like separate building codes. And the one for bridges is called the B80, okay? And there's actually not a building code for structural concrete other than for bridges. So for like high-rise buildings and stuff, they still follow this code, the B80. It's the most like, what's the word? Strictest code. So these will follow like the strictest methods. I think there's different codes for if you're doing residential construction. There'll be like slightly looser regulations and things like that. But anyway, so the B80 It specifies that you need at least 2 concrete vibrators in case one breaks during the placement or doesn't work or whatever. And you need to vibrate the concrete for like 7 seconds or something like that. So that's like the duration that you vibrate the concrete so that it's not under vibrated or over compacted. She used the word compacted. Okay, any questions? So that's like buildability stuff. Okay. So the idea is that, remember with like your high slump concrete, you don't need to vibrate it very much for it to basically be fully compacted from like the moment it's placed. So the moment it's placed is like partially compacted, and then fully compacted is once you've finished vibration. Whereas like something which is like a concrete mix which is designed for like pavements or slope surfaces, you'll need to vibrate it for longer or whatever, okay? Okay, so that's basically how that works. Okay, so for slabs, we're specifying this slump. That's basically what the question was asking from us. Do you guys have any other questions about that? Okay. So, question 6. Why is curing important? And what are 3 important factors affecting curing, and discuss them? So this is more of a recap of what I said last time, because I kind of answered this question already through explaining it. But we've got the factors affecting curing being moisture, temperature, and time. And we've got some graphs to describe that. But ultimately, it's to do with evaporation, right? So when you've got fresh concrete and then it starts to set and becomes hardened concrete, you need to basically combat moisture loss, right? Especially from the surfaces exposed to air and sunlight and things like that, as this causes plastic shrinkage. If your concrete is starved of water, it can lead to reduced strength, okay? That's basically ultimately what this is talking about. Any other questions about that? So this is all, like, remember, this is all last week's stuff to do with concrete placement and things like that. Okay, question 7. Why is a flexural test more preferable to a splitting test or direct tensile test? Okay, so it's more accurate to real life conditions, and I would like to elaborate on this a bit more than what I was talking about last time. I'm just really like paranoid I'm on the wrong document, but I'm on the right one. I'm not on my master copy. Okay, so when you design reinforced concrete members, like you have to kind of understand the pros and cons of using concrete specifically as material, or reinforced concrete over, say, steel or say timber. Okay, so a lot of the time, and this is like not a hard and fast rule, if you have something like a truss, okay, and let's say that truss is taking a point load at the top, you're going to have members which are in compression, and then you'll have members which are in tension, for example. And since it's a truss, you're assuming only axial forces are traveling through this structure, okay? But we haven't picked the material or specified a material yet, right? But generally, these trusses are not made of concrete. Now, again, that's not a hard and fast rule, but a lot of the time trusses are more well suited for something like steel or something like timber. Because remember, if you think of a material curve for steel, this is stress versus strain. Steel is just as good as it is in tension as it is compression. But if you think of it in terms of the concrete material curve, right? Concrete, let's say tension's up here. So going up is tension. Concrete's actually very weak, okay, in tension compared to its compressive strength, which we'll go to explain a bit more later this lesson. But the point is, where you generally use concrete is not so much for trusses, more so for things like beams and columns, okay? So if instead of a truss structure, we have a frame, let's say, and this frame is, let's say it's taking a uniformly distributed load, you've got these members acting as beams, and you've got these members acting as columns, okay? So the beams, right, essentially their primary purpose is flexure, so that would be the bending moment diagram. So they're mainly taking bending and shear. Okay. Whereas your columns are primarily taking axial forces, right? Like compression. Okay. So these are both purposes. Both purposes of beams and columns are quite well suited for reinforced concrete. Okay. So when we say that, going back to the actual question, when we say that a flexural test is preferable to a splitting test or a direct tensile test for reinforced concrete, and the fact that, or for testing concrete rather, and the fact that it's more accurate to real life conditions, what we're saying is that we don't generally specify purely tensile members for concrete. It would not be very smart. It's not very suited for the material. Instead, we specify things like beams, right? We're looking at this beam. Let's just say it looks like that or whatever, which has like that bending moment diagram and stuff like that. But the idea is that in positive bending, so it's positive bending, your beam is basically taking both compression and tension. Okay, so the idea is that in this particular scenario that I drew, for the portion of the beam that's in positive bending, the tensile side of the beam is taking tensile forces, right? You still need to test like how strong the concrete can behave in tension, but not exactly pure tension. It's called flexural tension. Okay, it's where you've got flexure, which induces tension, or bending, which induces tension is another way of saying it. Okay, so yeah, that basically is why we were talking about the 4-point bending test from last week. Again, just to remind you, that was this part. So that's how they would test for that flexural tensile test, flexural tensile strength. Okay. And as I was mentioning before with my weird example about like Leonardo da Vinci and all that crap, the idea is that you've got this kind of size effect, right? When it comes to concrete and ceramic materials, where essentially if you have some like a larger sample of this material, like concrete, or like a rope that's being pulled, like an iron rope or whatever, you've got a larger sample, it's a longer rope, it's got a higher chance of micro cracks being present, which can induce fast fracture. All right. Anyway, so yeah, that's why we would use the 4-point bending test as a more representative sample for the concrete strain. Okay, any questions about that question? Nope. Okay. Cool. Question 8. So this is the last question from last week. During the class, we briefly discussed load and displacement control testing. Briefly state the difference between them, which is better to obtain strain softening behavior. This would be more of a recap of what I said last week because I kind of already mentioned this. But the idea is that, yeah, when you have a force-controlled test, it's basically treating the amount of pressure that you crush the concrete cylinder with as your independent variable. So it's like, okay, like we're going to measure the dependent variable, which is the strain, based on this dependent variable. Okay, so like let's just say, for example, you go over here is like 0.3 MPa or whatever. We measure, the point of strain at 0.3 MPa. And then we increase it, 0.6 MPa. Then we measure the corresponding strain, etc. So the problem with treating the force as like the independent variable is that it can't be undone. Do you know what I'm saying? Like you can only increase the force, and so therefore it doesn't know that, like it doesn't know when to stop applying like an increase of pressure. Okay, and so it doesn't effectively capture the material curve past this point, which it reaches its peak stress that it can handle, right? So for displacement control tests, it works the other way around, where your independent variable is your strain. Okay, so it's like we're moving the machine by this much, which let's just say 0.005 millimeters per second or whatever, so 0.005. Oh, well, this is in strain, so it's unitless, but anyway, you kind of get the idea. Whatever equivalent for the strain would be. Yeah, so you change how much the press has moved, and then you measure the stress response. So how much pressure is it pushing back with, okay? And so this way, it captures the entire material curve, including the post-peak behavior, all right? This being the peak. So it captures everything over here as well. And this way, it's also less dangerous and explosive, okay? Any questions about that? Okay, great. Okay, so that brings me to workshop 3. So again, the stuff that we'll be talking about and like focusing on this workshop will be shrinkage, admixtures, and concrete properties, okay? So my current plan is to try and squeeze in everything from there in the first half and then give you a break and then these ones. But now that I'm looking at it again, what I might do is I might give you a break off, like before I do any questions because of how the timing might work. Anyway, okay. So course structure. So we're up to week 3 now. Yep. And next week we'll be starting with like design and telling you about how steel and concrete are integrated together. But for now, we're still mostly focusing on the concrete material itself. Yeah. And then from week 5 onwards, we're gonna be focusing on basically, well, the way they'll work is these 3 are kind of related to the design of beams, which we'll go through slowly. And then this one is your slabs. And then this one, of course, is just columns. But what you'll realize is that the idea of flexure will tie in, and serviceability will tie into slabs as well, okay? As well as flexure will tie into columns. So you're kind of just acquiring like the bits and pieces through like learning about beams, and then you'll see how it's applied in terms of slabs and columns too. So that's kind of how the course is structured, okay? All right, let's talk about shrinkage. So first I'm going to talk about plastic and drying shrinkage, which are closely related, before talking about chemical shrinkage, okay? All right, so plastic and drying shrinkage, essentially these terms are related. It just depends on when the shrinkage happens, whether it's when your concrete is still like in a liquidy state or fresh, it's called fresh concrete, or whether it's hardened already, okay? So for fresh concrete, when shrinkage occurs, we're talking about plastic shrinkage, or rather the physical shrinkage is referring to the plastic shrinkage. Whereas for hardened concrete, it's called drying shrinkage. Okay, so what is shrinkage? It's basically due to a loss of moisture, and this essentially happens kind of in 2 parts, right? And then there's like a result, sorry. So, okay, wait, maybe I'll write it like this. Okay, so the idea is that as you're pouring the concrete, water will start to bleed to the surface or rise due to capillary action and things like that. So that's the water physically rising, right? That's just one side effect of how, like basically the aggregate of rock, so the aggregates within this concrete mix are heavier than your water, right? So they'll want to sink down to the bottom and the water will want to rise up because it's less dense, right? And essentially, because you've got excess water like towards the surface, you're going to get surface evaporation, especially if you don't treat for it, right? So if you're not spraying your water like every now and then or whatever, and just keeping the top surface moist, you're going to have excess surface evaporation. Okay, so that's the physical things that happen. In terms of shrinkage, if you think about shrinkage, all right, so I'm just going to draw like a generic square or rectangle. You're thinking of the idea of area or volume loss, I guess, depending on how you view it, right? So if you're viewing it from 2 dimensions, it's like an area loss. From 3 dimensions would be a volume loss, okay? Now, this might imply that it's caused by some kind of like compressive pressure, right? And I guess to some degree there is that, but more so if you think of concrete as like blocks, right? Like a block of chocolate or something. If all of these are shrinking at a certain rate or whatever, like shrunk by a certain amount, Now you see that there's going to be like spaces between these, okay? So the idea is that we're more concerned about the reactionary tensile stress that it pulls, that it, like, I guess, results in, okay? So because all of these like bits of concrete want to pull away from each other, right? That's where you've got a problem, because the tensile strength of concrete is quite weak, and so you get cracks that form, okay? So this would be like a crack, for example, right? So that's what shrinkage is ultimately referring to. It's the idea that because of your concrete like pulling in, there's going to be these tensile rips that occur, right? And that's a crack. Any questions? Oh, sorry, and that's basically what I was trying to explain. That's basically what I was trying to explain there. So you got shrinkage, it induces these tensile stresses, which results in the concrete cracking, okay? Any questions about that? Nope, okay. So shrinkage. Thermal expansion. I think this will make more sense in the context of a question, which there will be one coming up. But this is the idea that there's a formula which we can apply from physics, which includes the coefficient of thermal expansion, which will tell us essentially the amount of, what am I trying to say? The amount of change in length or change in area or whatever. Okay, so if we're measuring concrete in one dimension, and let's just say that is L, okay? The idea is that if the concrete is shrunk by some amount, right? This is delta L, or in the context of how we've written it here, lowercase delta, okay? And we're talking about this kind of contraction, let's say, in terms of one dimensions, okay? Now the strain is the same thing, except if you remember, strain is equal to the original length, no, it's the other way around, the change in length over the original length, okay? And so essentially what we're doing is we're just dividing by L, right? So if you cross that L out, that's the thermal strain. So these are just two ways of saying the same thing, okay? The thermal shrinkage, like change in length, versus thermal strain, which is just normalized by the total length. Anyway, I was kind of yapping. Does that kind of make sense? All right. Okay, let's talk about chemical shrinkage. So chemical shrinkage can be defined as the volume reduction due to hydration of the cement. So remember, you've got your alite and belite and all these cement minerals, and then when you add water, they get hydrated, and then there's like there's chemical reactions that happen essentially, right? The idea is that because of this chemical reaction, there's going to be some amount of volume shrinkage in our concrete, okay? Now, you can break this down to three parts, okay? The first part is the chemical shrinkage at the initial set. The second one is the autogenous shrinkage, aka the internal drying. The word they use as well is self-desiccation. And then the third part is the voids generated by hydration. Okay, so let's visualize this using the stuff that they provided in lecture slides, but I don't really like how they point at stuff in these, so I've kind of like repointed at certain parts, okay? So let's look at the one on the left first, okay? So in terms of the initial chemical shrinkage, when you cast the concrete, so you've poured it on site, after a certain amount of time, it starts to set. So let's say after 30 minutes, it starts to set, okay, after you've poured it. This, between when you've poured it and when it starts to set, some of the hydration products have been formed, okay? So the hydration reaction is like already starting. This is the initial chemical shrinkage, so that's part one, okay? Now, after the concrete hardens, okay, so this could be after, say, 24 hours or like a day, right? Let's say it takes that long to harden. So good. Is that a good amount of time? I'm trying to think. Yeah, okay, let's say after 24 hours. All right. Essentially, you get these bubbles generated by the hydration reaction. So over here, when the cement was still turning into, like, when the cement was still consuming the water and then turning into the hydration products, there wasn't enough hydration products to produce a significant amount of voids, okay? So these voids generated by hydration, I didn't talk about autogenous shrinkage yet. Okay, let's talk about 3 before we talk about 2. Okay, what I'm talking about right now is number 3, which is the voids generated by hydration. So the idea is that there's all these voids there's all these voids generated by hydration, and if you were to take them out, right, then that proportion is essentially part 3. It's the voids generated by hydration. So if you were to visualize it by taking all these voids out, this block of air is part 3. Okay. So next is the autogenous shrinkage. So this is actually, sorry, I should have gone the other way around, but this is actually what happens between the initial set and then hardening. Okay, so as a matter of fact, it was this which goes to the hardening stage, and then this was the internal drying that happens. Okay, so these are 3 separate things, and when you add them all together, part 1 plus part 2 plus part 3, that is the definition of your chemical shrinkage. Okay, so let's look at this from another angle, which is this other graph. So this is the volume reduction, aka the shrinkage, versus time. Okay, so between when you've cast the concrete and when it starts to set, you've got the initial shrinkage. Okay, and then essentially there's 2 kind of processes that happen. All right, there's the autogenous shrinkage, the internal drying, which results in like the volume reduction, and then there's also the voids generated through hydration, which is more significant. Okay, so that's that block from all the voids generated through hydration. But the sum of all of those, that whole bracket there, is your chemical shrinkage. Okay, does that kind of make sense? I know this is in your quiz, and I know the wording is really annoying. So please read your questions in your quiz very carefully, because each one's trying to basically like word it in a slightly different way, and they're trying to test your understanding of this concept. Okay. All right. Let's continue to admixtures, unless anyone else has any questions about shrinkage. Yes.
So is the difference between drying shrinkage and chemical shrinkage? So drying loses water
Yes.
through just like physically losing it through evaporation and through bleeding, and then chemical, it loses water from its chemical reaction, like it's being consumed.
Yes. Okay. So okay. Plastic and drying shrinkage are physical, and when we say a loss of water also implies a loss of volume, right? The water's gone, and so therefore you get shrinkage, which is a loss of overall volume. Okay. For a chemical reaction, yes, you're right. Essentially, when the water's consumed, and then you get these air bubbles and things like that, that is also a measure, like there's some amount of overall volume reduction associated with that. And so that's the chemical shrinkage portion. Okay. Yeah. Okay. Sorry. I'm not the expert in this topic. I can't lie, but I think for the purposes of your quiz, just try to read the question as carefully as possible and try to come to a logic that you're satisfied with in terms of how to answer the question. Okay, sorry. Yeah, sorry. It just takes a lot of like rereading it over and over again because it's a very, very subtle difference. Okay. Any other questions for now? Okay. Let's talk about admixtures. So admixtures can be broken into 2 categories. You've got chemical admixtures and mineral admixtures. Okay, so in terms of chemical admixtures, I've included kind of 2, but kind of 3 examples. Okay, so you've got plasticizers and super plasticizers, and super plasticizers are essentially just plasticizers on steroids. Okay, the idea is that you can reduce the water content by adding in these plasticizers, and it will affect like the workability essentially. Okay, so without adding more water, you can essentially make your concrete more runny. Okay, so that's a plasticizer, and super plasticizer is that, but on steroids. Okay. Okay, like you don't have to add in as much of a super plasticizer to get the same effect as the plasticizer does. Okay. So air entraining agents would be something to add in, which produces more air bubbles around the pores. Okay, which sounds like it wouldn't be beneficial, but it's used in like niche scenarios where there's freeze-thaw cycles. So you actually want water to basically have a spot to get trapped and then removed through like the freeze-thaw cycles. So this is like in areas which is like snowy or very, very cold, things like that. Okay, because if you don't have these, the risk of freeze-thaw cycles is they can cause brittle cracking and things like that. Okay. Anyway, so air entraining agents was another example of a chemical admixture. So mineral admixtures, right? Another way of saying mineral admixtures is supplementary cementitious materials, or SCMs. So we've mostly been talking about OPC, so ordinary Portland cement, and this general blend of how we make modern day cement, essentially. Okay, well, just trying to think of the order which I talk about everything in. Okay, so OPC is essentially known as a hydraulic material. Okay, so we're gonna break up the mineral admixtures into three kind of categories, right? So you've got hydraulic minerals, latent hydraulic minerals, and pozzolandic minerals. Okay, so hydraulic minerals such as OPC, the general blend of concrete that we've been talking about, basically what makes something hydraulic, okay, is that it sets and hardens with water. So I'll give you an example of something that's not hydraulic. Back in the day, they would build things with mud, right, as the glue between like bricks or something like that. Okay, so mud is not hydraulic because when you re-wet mud, it like unhardens essentially, right? It becomes, it unhardens, right? Whereas for OPC, once you've wet it the first time, it undergoes that hydration reaction and sets. And when you reapply water, it doesn't undo itself, if that makes sense. So it's a one-way kind of reaction. Okay, so that's what makes something hydraulic. It reacts with water and then sets and hardens, okay? So this is a kind of dodgy chemical reaction, chemical expression. I wouldn't take it too literally. But when you add water to ordinary Portland cement, the idea is that you get these products, right? You get, and this is in cement notation. So you get your CSHs, which is like basically a category of products, right? But they're the main glue, right, for your concrete, okay? But and that's ultimately what we want in order to have more strength, okay? We want this product. However, it also produces CH, the C standing for carbonate, I think, and then H standing for hydroxide, okay? So this is essentially a byproduct, and essentially it can be a problem because it reacts with the sulfates and expands. So if you remember from last lesson, I was talking about the fact that soil can have sulfates in it, right? Actually, it's kind of funny, right? So basically, so imagine you've got, there's like some dirt, right? And then here's dirt with sulfates, okay? So this is just regular dirt, but dirt with sulfates is called acid sulfate soil. Okay, if you abbreviate it, it's ARS. Okay, but they actually never call it ARS. They call it potential. Okay, so they don't like to call it ask, they call it pass. Okay, or pass. All right, just so you know. All right. Anyway, so when you have sulfates from the soil, right, it can react with this product, right, the carbonate hydroxide or whatever, and then cause expansion. And then we talked about last week that this like leads to spalling in the concrete. Okay, so it's no good. So we want to get rid of it. Okay. However, it does have some upsides. Okay. One thing is that it's highly alkaline. So again, something that I mentioned last week is that we've got a pH scale to pH. Water's at like 7. Something acidic would be over here. Oops. And something like fresh concrete is over here, right? This is alkaline. And what makes it alkaline is this CH, okay? So this helps the brown rust to form on the Rio, as I mentioned last workshop. So the other thing to realize about CH is that you can essentially consume it, or yeah. Oh, right. It helps if I bring up the previous week's stuff. Okay, so to recap. Okay. Essentially, there's 2 types of corrosion, okay? There's your initial kind of like, okay, so you've got a bar. Wait, is this my copy? Okay, good. You've got a steel bar, okay? And it's exposed to like the air and it can oxidize, like so. All right. What I'm trying to say is that this oxidation layer, the brown rust layer, is actually beneficial because it's a shield that prevents further corrosion. The type of corrosion that we don't want, essentially, is the second type, which is called pitting corrosion, which can happen due to chlorides and stuff like that. So when chlorides react with this brown rust layer, this oxidized layer, it can eat away at the steel cross-section, okay, and corrode it. So that's the kind of corrosion we don't like. But the type of corrosion we do like is brown rust because it's actually a protective layer.
What does it protect against?
It protects against corrosion because otherwise it protects against the second type of corrosion. Because if you just have steel by itself, I forget the name of the chemical process, but the idea is that corrosion can happen when it's just like pure steel exposed by itself. Yeah. Sorry, I don't have a great explanation. Yeah, for that. Yes. And then I kind of explained this last time, but I won't get too much into it this lesson. Yeah, all good. Sorry. Yeah. Okay. So the idea is that you've got this byproduct, right? The CH, which is not directly what we want. All we want is CSH. You've got this extra CH lying around, but it works well with the other mineral admixtures, which I'm about to talk about. Okay, so the other types of reactions. So one type of reaction it works well with is a latent hydraulic reaction. Okay, so again, hydraulic reaction means it reacts with water and then sets and hardens. Okay, latent hydraulic materials or reactions do the same thing, but they need to be activated somehow. So latent just means there's potential for it, okay? So what conditions do we need for these other things to basically produce a hydraulic reaction? Okay, so a type of mineral admixture that we use is blast furnace slag, and I'll explain that more in the next slide. But let's just say when you have slag with water, right, this is a latent hydraulic reaction. So what we need in order for this reaction to happen is CH. Okay, so this byproduct, which came from OPC and water, can activate slag to also become a hydraulic reaction, okay, or it can activate it and for it to become a hydraulic mineral, okay. Okay, it's called an alkaline activator because we mentioned CH is highly alkaline, which helps the brown rust layer form on the Rio, but it also produces this alkaline environment, which allows for slag and other similar mineral admixtures to basically activate and then undergo their hydraulic reaction, okay? All right, so that's what I'm trying to say with the synergy, okay? So when you have OPC, it also benefits, you basically need OPC for slag to be activated, okay? All right, now the other type is pozzolanic minerals, okay? So pozzolanic minerals actually consume the excess carbonate hydroxide, right? So this CH that was produced from OPC can actually be consumed, right, to create more of the glue product that we actually want. So as you can see, the hydraulic reaction produced from OPC synergizes very well with slag and your pozzolanic materials because since it produces CH, basically in the presence of CH for slag, it gets activated, and then directly consuming the CH for pozzolanic materials, it also produces this glue product that we want, okay? Does that make sense? So that's the three types of reactions that we're going to look at, okay? All right. So here's some examples. So I mentioned before like slag, but I'll just show you this graph. Okay, so this graph has a measure of your pozzolanic effects and your hydraulic effects. And so with OPC, this regular type of cement, the entire thing is a hydraulic effect, okay? So it's the most hydraulic effect that we can get. For slag, it's a mostly hydraulic effect with some pozzolanic effect. And then you've got your fly ashes, and then you've got your, I think these are called the natural pozzolans, but it's in some types of clay. And then silica fume is basically an entirely pozzolanic effect. In other words, it requires CH to undergo the reaction, okay? So that's kind of how it works. Now, one thing I want to point out with this scale, since we've got this arrow here, we've got the increasing calcium content. Now, the reason this is important is because if you remember, in the hydration of OPC, we produce a lot of carbon dioxide, okay? So if you have a hydraulic effect that happens, right, it will basically, it implies that it is a chemical reaction that produces a lot of carbon dioxide. Okay, so it's no good for the environment, basically, right? The idea of adding these mineral admixtures ultimately is to have a more, I guess, like environmentally conscious, like cement mix. Okay, so if you blend in these other like SEMs, you can basically produce less carbon dioxide when you hydrate the cement. Okay. All right, so I'm going to teach you how to read ternary diagrams. That's actually a lot. Okay, you know what? Sorry, before we get to the ternary diagrams and then this table and then the questions, I might give you guys a break because I've been talking for a long time. So how about we come back at 5+. All right, you got 5 minutes. Feel free to stretch your legs and grab some water and go to the bathroom and stuff like that. Okay. I'll go 6+. Yeah. Yes. All right, guys, let's continue. Oops. Checking it's still working. Yeah. All right. So, ternary diagram. So if you did geotech last term, this might give you flashbacks. We've got basically a measurement of 3 separate chemical compounds on this ternary diagram, and then the proportion of it. Okay. So the first one is calcium oxide. Okay. What did I say before? I don't know what I said for C, but I meant calcium oxide. I think I might have said carbonate, which might not be right. Anyway, C is calcium oxide. Okay. So you got calcium oxide. You've got aluminate, and you've got silicon dioxide. Okay. Aluminum. Anyway, you got these, right? So, oops. So, how do you read this? Well, what you do, and actually what I've done is I've kind of overlapped this kind of scale onto it, right? So, what you've got underneath is the different types of mineral admixtures, all right, and then plotted based on the ternary diagram. Okay, so what I had moved off to the side, this is just a generic ternary diagram. Okay, so it can apply for different compositions as well. Okay, so all right, essentially, if we're told that this is the composition, or rather, actually, let's go the other way around. If we're looking for slag, for example, right, and then trying to find its ratio of these three compounds, it's over here. Okay, so for SiO2, right, that's over here. We're measuring SiO2. We're measuring this way. Okay, so at 50%, all right, we care about it going that way. And then for CaO, right, we care about it going this way, and it's at 20%. So over here. And then for AlO3, that's this one. We care about it going this way, so 30%. So we've reached this point here. Okay. Wait, that doesn't make any sense. Why does that not make sense? Why does that not make any sense? 20, 30%. Why is it not over here? Maybe I copied down the wrong numbers. Okay, let's do it the other way. So sorry about that. Okay, I don't know. I have to double check these numbers that I wrote down. But for slag, all right, we've got 50% CaO. Okay, we've got 20% Al2O3, and then we've got 30% SiO2. Okay, so I must have switched these around. Sorry. That's supposed to be 20%. That's supposed to be 50%. That's supposed to be 30%. Okay. So anyway, that's how you read a ternary diagram. Okay. So follow the direction of the arrow and follow these kind of markers in terms of where to go. All right. All right. Anyway, so yeah, what you'll see is silica fume is incredible. Like it has a high proportion of SiO2. OPC is over here, and it has a high proportion of CaO, right? And then you've got the spectrum of other things as well going on. CSH is your glue product, right? And it's just telling you that it sits over here, okay? All right, any questions about how to read that? Okay, there'll be, I think there's an example of it as well in one of the questions. All right, so we've got a table of admixtures, and essentially, I'll just go through like their pros and cons essentially. So when we say admixtures, we're talking about things that aren't OPC, because OPC is the default. All right, so checking I'm on the right document. OPC is the default, right? And you need OPC in any cement mix, because the OPC reaction creates this, right? It creates CH, and CH is used by the other types of reactions, okay? So it's called an admixture because it's just like little bits of these other minerals that you're going to sprinkle in, okay? So slag, in other words, ground granulated blast furnace slag, basically the idea is like you have to think about kind of the whole life cycle assessment thing for all these like different manufacturing processes, right? So for slag, this is a byproduct of iron manufacturing. So because we're not specifically trying to produce this slag, right? We're trying to produce iron, and as a byproduct of that manufacturing process, we get this kind of relatively useless byproduct. We get that byproduct and we use it in our cement manufacturing process. So this is like the whole idea of a circular economy and why you can kind of reuse these kind of byproducts, right, in other processes. Okay. So this slag, as I mentioned, it's latent hydraulic in terms of its reaction. It's got a high calcium oxide content, and it's got angular particles. All right. So what are the kind of pros and cons? All right. So when you add this in, it increases workability, which is neutral depending on your kind of what your purpose is. It increases the set time, which is generally not good. It reduces the early strength, which is generally not good. The acid sulfate reaction, acid sulfate reaction resistance is increased, which is generally good. It makes your concrete more dense in the end. It increases the bond, which is generally good. Hydration heat is reduced, which is generally good. And then the permeability is decreased, so there's less voids. Okay. So anyway, like a lot of these are like, they're not really pros or cons, they're like mostly neutral. But they'll change the ratio of aggregate and water and stuff that you add in, and things like that. Okay. All right. So fly ash. So fly ash is, and there's going to be two types, right? There's class F and class C, and class F has like a low proportion of calcium oxide, whereas class C has a high proportion. Okay, this is a byproduct of coal-fired power plants, right? And this is a mostly pozzolanic reaction. Okay, so we're sitting here and here, so this is the fly ash, and like these are your pozzolans, basically, right? Anyway, so yeah. Should I go through this entire table? I don't know. Maybe I'll just go through like the important stuff. So there's fine, smooth particles, like the fly ash. It reduces the pH level, which is not good because you generally want an alkaline environment for your brown rust to develop. It increases creeping, which is kind of like a structural property, which we'll talk about maybe in like week 8. Yeah, there's like a bunch of random stuff that happens when you use these SEMs. Okay, silica fume. So this one's like the most different from OPC, right? Because where OPC is like over here in terms of its calcium oxide composition and in terms of its like the fact that it's a fully hydraulic effect, silica fume is on the complete other end, where it's a pozzolanic reaction entirely, right? It's a byproduct of induction arc furnaces or silicon, but it's essentially required for high strength concrete. Now, this is like a super, it's a super fine particle, and yeah, like it's probably the most extreme admixture that you can add, right? So the strength is significantly increased when you work when you add this in, but because it's made of these very fine and smooth particles, it becomes more sticky, right? There's more surface area, and it reduces the workability. What else? Yeah. Anyway, these other things that happen, but those are probably the two most important ones to focus on in terms of what happens to your concrete mix. And then there's also natural pozzolans. Natural as in it's not a byproduct of anything. It's found naturally in volcanic tuff and ash and pumice and things like that. Yeah, this part of the table is not really covered in the course. Sorry, in the lecture slides. But also, I think the most basically the majority of what you got to focus on in terms of SEMs are these 3 types, but really there's 4 types because there's 2 types of fly ash, right? Okay, any questions about that? That's SEMs. Oh, okay, let's do some questions. All right, so questions 1 to 5 are to do with the shrinkage, like the stuff to do with shrinkage, and then I think question 4 and 5 are to do with SCMs. Okay, so question 1. Briefly discuss plastic shrinkage and the main cause of plastic shrinkage. So remember, where plastic shrinkage sits is in terms of like the physical shrinkage, right? So not to do with chemical shrinkage, and essentially, yeah, it's when you have fresh concrete and then there's like evaporation, which causes the shrinkage, and then it induces like cracking and things like that. All right. Question 2. Discuss 3 shrinkages in the class and what is the main cause of such shrinkages, right? Okay, so part 1, let's discuss drying shrinkage. So drying shrinkage is when you've already got hardened concrete and you've got this evaporation or loss of water. It affects the cement portion of the mix, right? By basically like increasing the relative amount of aggregate that you've got. Oh, so sorry. Since drying shrinkage affects the affects the cement portion of the mix only, if you have more aggregate than cement, you have less drying shrinkage. Okay, so that's one way to reduce the effects of drying shrinkage. And it's caused by ambient or environmental conditions such as, say, like sunlight or something, right, causing evaporation. All right, so that's drying shrinkage. Chemical shrinkage. Okay, so so the hydration reaction of cement, basically, what am I trying to say here? The volume of products is less than the volume of reactants, right? I don't know what else. I don't know what to smoke in there. Okay, let's read the next line. Before setting, you've got the macroscopic shrinkage, right? Which is the amount of shrinkage. Sorry. Fuck. The hell am I? It's this basically the chemical shrinkage at the initial setting. Okay, so the part 1 of my diagram. Okay. After the setting happens, right, you've got the formation of these internal capillary pores, right? And ultimately, the chemical shrinkage is combining those two things. Okay, so I think what I was trying to say there is there's this one, and then there's these two combined. So that's what part 2 was in that answer. Okay. So in terms of autogenous shrinkage, it's a subset of the chemical shrinkage, right? So in my explanation above, it was the part 2. It's due to the self-desiccation, right? And then here I've got a bit more formal of a definition. When there's no access to the outside water and you've got a sealed system, the formation of internal pores due to hydration causes an internal humidity drop, which results in the internal drying. Okay, so I probably should have just said that word for word or something earlier when I was trying to explain autogenous shrinkage. Okay, I'll leave that on the screen if you want to copy that down. Okay, so in terms of the differences between chemical and drying shrinkage, which I think was kind of what you were asking earlier, Alex, right? Chemical shrinkage is the loss of water due to hydration, and it occurs once the cement, only once the cement and water mix together. Okay. And then chemical shrinkage has the macroscopic component and the internal shrinkage component. All right. In terms of the drying, right? So the physical loss of water, such as evaporation, it's macroscopic only. Okay. What the hell? Okay. This is kind of just wording what I was saying earlier, but differently. Okay. So it's kind of, yeah, anyway, it's kind of confusing to me because it's not the way that I would word it.
Would you say
Yes.
the difference between, so I guess my like understanding about everything is, so there's drying shrinkage, which once again is just the physical loss of water.
Mhm.
Then there's chemical shrinkage where water is consumed in the physical reaction, leaving like voids, like not air pockets, but like just bubbles in the cement. And then there's exogenous shrinkage, or however you say it.
Yep.
That's just internal drying. So all of the processes of just different ways of losing water.
Yes, but the second one that you said, only like is only talking about part 3, all the voids generated by hydration, right? And then the autogenous shrinkage, yes, it's internal drying, but it's still chemical related, right? But yes, they're all something to do with water, and it's all results in a loss of volume, which is ultimately what shrinkage is, right? And the mechanisms can either be classified as chemical or physical, right? Yes. So yeah, the autogenous shrinkage was just one part of the chemical shrinkage, okay? Yes. Okay, sorry. Not a great explanation on my part, I can't lie. Do you have any more questions before we move on? Okay. Let's move on to an example to do with, like, I suppose, yeah, it's like a shrinkage related question, all right? So this actually has some calculations. We're placing a 20 centimeter thick concrete parking lot with joints spaced at 5.5 meters apart. We thought that we need some thermal expansion joints to account for the thermal expansion when the concrete gets hot in the summer. Engineer insists expansion joints are necessary. Has he lost his mind, or is there a compelling reason for no thermal expansion joint? All right. The following information can be used. Coefficient of thermal expansion for concrete is 10 microstrains per degree Celsius. I'll explain that in a second. And then it's saying even low shrinkage concrete shrinks at about 0.05% of the length. Let's say the maximum temperature difference in a year is about 30 degrees Celsius, okay? So, okay, let's break this down. So first thing is that when you see, let's just talk about it in terms of, when you have a large block of concrete, let's say, okay? So you've got concrete like so. Which way do you expect a crack to form and where? You will expect a crack to form somewhere there, okay? The reason is when you have shrinkage, all right, like so, all these bits of concrete are trying to pull away from each other, right? And so if this dimension is significantly longer than this dimension, there will be more tensile stresses going this way, and so the crack will want to form where there's the largest tensile stress, right? So generally in the middle is where it's accumulated the most, okay? So in order to combat this, right, you basically have designated spots for cracks, quote unquote, right? So that same block of concrete, instead of a crack forming due to shrinkage, you would instead put something called a joint there, okay? So a joint is basically a predetermined spot for a crack, right? So it's just a place where the concrete is separated. So that's a man-made crack, essentially, right? But it's nice and even, so it doesn't look ugly, okay? So when the question says the engineer insists that expansion joints are not necessarily. What am I trying to say? When the engineer insists that expansion joints are not necessary, what it's saying is that this particular concrete parking lot doesn't need joints, okay? We need to do some calculations to figure out whether that's true or not, okay? So let's break down these little dot points first. So the first one's saying that concrete has 10 microstrains per degree Celsius as its coefficient of thermal expansion, right? So that's this. So 10 being like a material value for concrete. Okay, so concrete generally has between 8 to 12, right? So this particular question just says take it as 10. Micro, which is this Greek letter, micro refers to times 10 to the power of -6, okay? And then strain is unitless, okay? And then degrees Celsius is degrees Celsius, okay? So yeah, he's saying, the question says even low shrinkage concrete shrinks at about 0.05% of the length. So what we're saying is we're establishing the max allowable shrinkage, okay? So when you use low shrinkage concrete, 0.05 as a percentage, okay, you have to divide it by 100 to get it as a actual decimal. and then we multiply it in terms of the overall length, right? So, okay. What it's saying is that in this parking lot, right, our joints are already at 5.5 meters apart. In other words, let's do it in terms of millimeters, right? 5,500 mil apart. We don't need to further break up this block into, like, we don't need to further divide it, okay? So the idea is that we put in 5,500 in terms of length, and then that gives us a number for the max allowable shrinkage, okay, before it cracks. Okay, so in terms of the actual shrinkage now that we're calculating, we input this formula, right? So this was specifically the formula for if we wanted to measure it in millimeters rather than as a strain, okay? So this is if it was a strain, this is if it was in millimeters. So we plug in 10 times 10 to the negative 6, all right, for our coefficient of thermal expansion. We plug in 5,500 millimeters, right, to get the whole thing in millimeters. And the change in temperature between the hottest and coldest periods of the year, it's said to be 30 degrees Celsius, right? So that's the max amount of expansion difference that it could have, right? Or expansion and shrinkage difference, okay? So that will cause like delta to be 1.65 mil, okay? So when we're comparing the actual shrinkage of 1.65 mil, right, between the hottest and the coldest periods of the year, it is less than the max allowable shrinkage, which was 2.75, right, millimeters from what we calculated using the low shrinkage concrete. And so therefore, it's okay without expansion joints if you use the low shrink concrete mix, which they specified in the question, that one. Okay? Any questions? So that question is basically just saying, it's like checking whether you need to add in expansion joints or not for this particular block of concrete, based on all this data that you're given. Okay. I don't think anyone else is still copying this down, so I'm going to move on. All right. Question 4. List 3 SEMs used to replace Portland cement, which were discussed during the class. Discuss the origins, discuss the effects, and the importance of the contents of amorphous glass in the importance of contents of the amorphous glass in SEMs. Okay, to be honest, I didn't read this part of the question, so I didn't include anything to do with it, but I'll talk about that next week when I have something prepared. In terms of the rest of it, it's just the table. So yeah, these were the 3 examples we focus on in the course, right? So it's slag, fly ash, silica fume, which are byproducts of iron manufacturing, coal fire power plants, and induction arc furnaces, okay? And then you can see the pros and cons and how they change the concrete mix there. All right. Any questions about that? Nope. All right, question 5. Please fill in the correct cementitious materials in blank and discuss the hydraulic and Poslandic effect. So the idea is that the question basically showed you this, and it didn't list what these things were, but yeah, it's just an exercise in like pointing at which thing's the right thing. So silica fume is the one with the most silicon dioxide, and then followed by natural pozzolans, and then you get to your fly ashes, which have increasing amounts of calcium oxide, and then you've got OPC and slag and stuff down here. Okay, that's basically that exercise. Yes.
Just the question changed from last year, so it's different for us.
Oh really?
Yeah.
Oh shit. What is that question about?
The plot below shows the blah 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 composition of major cementitious materials. Discuss the reactivity using this ternary diagram.
Okay. I will get back to you next week on the answer for that one, all right? I didn't realize the question changed. Oops. Can you tell I did this, like these are my notes from when I did it, did the course. All right. Okay, one last thing before we wrap up today. Now we can finally start talking about structural properties rather than these bloody chemicals, okay? So for concrete, why do we use concrete, all right? There's many reasons, but the best reason is that it's very economical, right? So we use a large volume of concrete, but per meter cubed of concrete, it's a lot cheaper to use than something like steel, okay? Concrete has sufficient compressive strength, right? So compared to steel, it's not as strong in compression, but considering how strong it is, it's still incredibly useful for us. Concrete is brittle and it's weak in tension, as we've discussed briefly. And so this is like kind of a weakness of the concrete material, which we have to address in our design. Now, probably the best trait about concrete is that it's incredibly durable, okay? So concrete is chemically stable and it's fire resistant, okay? So if you compare a steel beam to concrete, this is like quite a good comparison in terms of why concrete is so durable, right? So concrete compared to a steel beam is chemically stable because it doesn't rust, it doesn't corrode. Concrete is also very good against fire, like fire events, as opposed to steel, right? Because steel starts to melt and lose its strength very quickly in the event of a fire, whereas concrete is able to take on fire a lot better. It loses strength at a much slower rate, okay? So, yeah, and then essentially concrete can also have a very good service life and doesn't need very much maintenance if it's well designed. Okay, so that's why you see a lot of concrete used for footings, right, of buildings, so the foundation of buildings, and you see it used in like underwater kind of structures as well, because you're not going to send someone down there and do maintenance and stuff like that. So it's a very good material choice for something like that, okay? So concrete has all these great upsides. So concrete, in terms of the material curves of like the individual components, right? And this is something that I briefly brought up, I think, last lesson, but I'll explain a bit more now, is that if you consider its individual components, such as like the aggregate and the paste, concrete itself is in between those individual components for its stiffness, right? So the stiffness being the elastic modulus of concrete is somewhere in between, but the strength of the concrete is actually weaker than both the paste and the aggregate individually. So the main reason for that is because if you think about a matrix of concrete being made up of the aggregate and the cement, which binds it, essentially because there are basically planes of weakness in between these materials, right? Concrete does not actually, it doesn't actually reach the strength of the individual materials like the paste and the aggregate, because it has these weakness planes basically, right? Yeah. Okay. I think that's called the ITZ, the intertransitionary zone. So that's the planes of weakness, okay? All right, so overall, when you look at a concrete material curve, it looks something like this, okay? So you've got this weak kind of tensile behavior, and you've got this relatively strong compressive behavior for the concrete, okay? So I think the rule is that the tensile strength of concrete is approximately 10% of the compressive strength, okay? So it's 10 times stronger in compression than it is in tension. All right, so this is an important characteristic of it. All right, so in terms of measured properties, right, we've kind of discussed the compressive strength, and then we've got the compressive cylinder test to measure that. We've mentioned that there's ways to basically measure the tensile strength through the splitting test or the flexural tensile test, right? So those are measured properties. However, the thing I want you guys to realize about ceramics, right? So when we're talking about different materials, and you might remember this from Maths 1101, essentially, you can broadly categorize materials into ceramics, metals, polymers, and composites, right? So if we are talking about ceramics versus something like a metal, right? Ceramics, so if this is a matrix of ceramics, right? This can still apply to metals, but let's just, yeah, I'm just gonna talk about it in terms of ceramics. So this is like something like a clay bowl, for example, okay? So imagine a clay bowl that you have at home or something like that, okay? It has these micro cracks or defects within the overall like material, right? Which can lead to sudden failure. So sudden failure is known as brittle failure, okay? So it's a brittle material. So if I had these bowls, right? Let's just say you get 100 bowls from your cupboard at home, assuming you have 100 bowls, and I got them and then I dropped them on the floor, right? And then let's say that 50% of the time they broke, okay? And then the other 50% of the time they survived, right? So why is it that some bowls survived and some didn't? Okay, this is the whole idea of random microscopic defects within this ceramic material, okay? So ultimately, when we're measuring concrete strength, so going back to concrete, we have to account for the randomness or the probabilistic nature of these materials, okay? So there's a probability aspect to it, okay? So if we look at this curve on the right, essentially compressive strength, if we measure compressive strength on this scale, the x-axis, and we say that our like compressive concrete cylinder, so we've got a compressive concrete cylinder, in the best case scenario, let's say that, no, that's a pretty high number. Let's say that it measures at 50 MPa. Okay, so your very best concrete cylinder out of 100, right, that you've measured, can sustain 50 MPa of load. Okay. Over here, let's say that the average, so if you did 100 of these tests, or dropped 100 bowls, let's say, the average is 40 MPa. Okay, so this is like a bell curve, right? The idea is that over here, right, you might have 32 MPa, let's say. When you see this notation, right, F-C, the dash refers to this idea of a characteristic strength, okay? So it means your fifth worst if you dropped 100 of them, or like, sorry. If you crushed 100 cylinders, the one that performed the fifth worst is your characteristic value, right? And that's the value that we use in our design, okay? So we don't use the best one, we don't use the worst one, we use the fifth from the worst one, okay? So this is conservative, but it's not overly conservative, okay? So if you use the very worst one, you might be overusing or over-designing with materials, okay? So there are some values to basically, like there are some like variable names that you should get familiar with, right? So F subscript CM is your mean, right? So that's the middle of this bell curve, your mean compressive strength. F-C is your characteristic. Sometimes called the fifth percentile. And then, yeah, that's pretty much it. Okay, those ones you should get familiar with. I think I've written them here. So that's the characteristic, that's the mean. Okay, and then the other thing is the margin. So the margin is basically this distance here, right? Or distance in terms of compressive strength, okay? So it's 1.64 standard deviations, right? From the mean is where the compressive, is where the characteristic compressive strength lies. You've also got all of these empirical relations. So these are ways that you can approximate one thing or another. And this is from AS3600. So from the concrete code, you can approximate the tensile strength, sorry, the flexural tensile strength through the tensile strength or vice versa. And then you can see all the other ones here. And then you can also approximate the elastic modulus, all right? So, oh, and then one more is the mean in situ compressive strength. So one thing that I haven't mentioned is that there might be another value here, FCMI. So the idea is if you've got the mean, right? So if we've got 100 of these cylinders which we've crushed, the one that performs in the middle, right, the median, anyway, the mean strength, right, is FCM. However, in a real life scenario where you're pouring the concrete, it will behave slightly differently than in these perfect lab conditions. When we have the subscript I of in situ, in situ refers to on-site, right? So if it's cast on-site, it has worse strength values than through the crushing test, right? Which is in perfect lab conditions. So that's why we're saying that the in situ strength is 0.9 of the mean strength, okay? And then there's this table from AS3600 as well, which give you standard values, okay? And then this is the density of concrete, okay? Any questions about these kind of structural or material properties? So this is saying that concrete is about 2.4 times heavier than water, okay? All right. So, I think we'll have time to do these last two questions. So these are kind of like qualitative questions that you'll, quantitative questions. So there'll be some calculations, and I'll show you how to do them briefly before we finish up the class. All right. So we've got 2 more questions to go. All right. A group of 85 tests on a given type of concrete had a mean strength of 38.9 MPa. Okay. So now we know that the mean concrete strength was 38.9 MPa. It has a standard deviation of 3.2 MPa. Okay, so S is equal to 3.2. Does this concrete satisfy the strength requirement for 32 MPa concrete? So when we order concrete, we're ordering the characteristic strength, right? So if I order 32 MPa concrete, I'm expecting it to basically be at least 32 MPa. All right, 95% of the time it should be above 32 MPa, okay? So does it satisfy it? And then use the 5% defective level, which means check whether there's only 5% defectives, all right? So essentially, F-C down here is equal to FCM, right, which is your mean strength, subtract by your margin. So your margin is 1.64 times the standard deviations, right? And so when you subtract one from the other, you get 33.652 MPa. So since this is greater than 32 MPa, right, we say that it satisfies the requirements. So if I ordered 32 MPa concrete and then we tested it and it ended up being higher, right, it ended up being 33.652, I would be happy with that, okay? Any questions about that? All right, so these are all statistical / probabilistic kind of calculations, right? So question 7 and our last question. Using the compressive strength results described in question 6, so we're going to take some information from the previous question. Estimate the characteristic uniaxial tensile strength, right? So F-CT. Estimate the characteristic flexural tensile strength, right, which is F-CT.F, okay? And the mean modulus of elasticity of concrete, which is EC, okay? So we're told from the previous question that we bring over F-C, which we calculated, and using F-C, we can actually plug it into these empirical relations that we have in order to work out the characteristic tensile strength. So the characteristic tensile strength is 2.09 MPa, and the characteristic flexural tensile strength is 3.48 MPa. Okay. From the last question as well, we know what the mean characteristic strength was. It was 38.9 MPa, and so we want to work out FCMI, and the reason we want to work out FCMI is because this helps. Sorry, I'll do it in a different color. This plugs into our equation to find the stiffness of the concrete, right? The mean elastic modulus. So what we do is we get let's do orange. We get FCM and we plug it into this equation, right? Giving us 35.01. Okay. So what this is saying is 35.01. Check if it's above or below 40 MPa. Since we're sitting below 40 MPa, we use this first equation here, and we can plug in the density of concrete as 2,400, and we can plug in FCMI as 35.01. Okay. Once we do that, we get that the stiffness of the concrete was 29,910 MPa. Okay, so I'll leave that up for you guys to copy down, but that gives us all the values that we were looking for from the question. Okay, that brings me to the end of the lesson. Thank you very much for your time, and yeah, see you next time.